is really a presentation about a project that the association has undertaken to try to help this sector of diversification for the water well industry. As many of you know, and I'm going to ask you here in a second, as many of you know, our industry is slowed down in water well construction, so some folks have been able to diversify into the geothermal sector, doing ground source heat pump installations of all scale, residential up to the large scale commercial projects. As an association, we're about groundwater first and foremost, so we advocate very strongly about make sure that these projects protect groundwater, and then secondly, we advocate very strongly that they be designed and installed properly so as to protect that diversification opportunity for the industry. Not only does the driller get an opportunity to diversify, but think of the supplier who's selling that driller grout and drilling fluids and drill rod and drill bits and all those other things that go into drilling a geothermal borehole, and of course the drill rig manufacturers as well. And increasingly, we think there's a role for the groundwater scientists to play, because we think oftentimes, certainly on the bigger scale projects, there is an assumption that the earth is the same the world over, and we certainly know in our industry that it is not. I gave a talk similar to this in another program, and I said, unfortunately, I think a lot of architects picture the earth like a block of wood, and you're just drilling in it and just putting a hole in it. Well, that is not how it works in the subsurface, as you all know. So what we're trying to do is see if we can't compile some fundamental tips that we would like the planners of these large-scale installations to think about before they go and start putting a lot of holes in the ground. And I'll talk about some examples here. I know that there's people in this room that are very experienced in this. One in particular claims to have drilled more geothermal footage than anyone else in the country. Right, Ralph?
I didn't say that.
Yeah. How much footage would you say you drilled over there? Hundreds of thousands of feet, certainly. Yeah, Ralph has been involved in this, and I've known him for a long time, a great part of the association and of the geothermal industry as well. So what happened is I was asked to give a talk at a EPA Region 1 conference, and I was there, and there was another presenter, and it was a consultant, groundwater consultant, and he was talking about a geothermal project that went bad. And where it went bad was driller was brought in to start drilling the boreholes for a school, and the driller encountered a gasoline plume on the site. And there's really no excuse for that to happen, because if they had done the proper geologic assessment, hydrogeologic assessment, they would have known that plume was present because it had already been detected once before. So that kind of got the wheels started. And then our local university, presently number 2 in the BCS rankings, the Ohio State University, decided to convert dormitories over to geothermal heat pumps. And they contracted with a firm from out of state, and they came in, drilled a couple test holes, thought they understood the property, and went to town, and they're using air rotary, and discovered that the formation that they were drilling in was karst, and they were losing circulation and wasn't going to work, and ended up in litigation, change orders in the $2 million range. That tends to make people at the universities very uncomfortable about spending more money than what was budgeted. And as the geology faculty at Ohio State watched that project, they realized there was tons of information available about that site if somebody had just made the additional effort to go and get it. So we're not going to fault those companies for what happened, and ultimately the project was completed and it's up and running and it's being used. But if there's something that we could do as an association to try to draw attention to these considerations before these projects got that far down the road, and do a little more thorough investigation of a site, that we might result in protecting that diversification and, of course, protecting groundwater. So we've started on this, and I give credit to Nina Baird. Nina is a PhD candidate at Carnegie Mellon University from the architecture school, but she has a real interest in ground source heat pump installations, and has been involved in that from an academic perspective on some open loop ground source heat pump installations. So some of these slides in there will be from her work. This is not going to be a description of guidelines. This is going to be a description of what we're trying to do. So that's why it's going to be short. And this is really an invitation to all of you because we're going to need reviewers and commentators on those drafts. So be watching for it, and we're going to recruit you if you're willing to and ask you to help us strengthen these to make them a better tool down the road. We believe that some of the most important and perhaps least understood variables in ground source heat pump installation designs are these, is that underlying geology, the presence of groundwater on the site, and the interaction between those and the building's HVAC system. And this is stuff that oftentimes the architects don't fully grasp. They don't understand what all this means to the building envelope and its heat loss and heat gain. And then what they're going to do is putting that heat in the earth and taking heat out of the earth as well. The questions that we ask is the typical installation have adequate geologic and hydrogeologic information to lead to, one, adequate groundwater protection, because again, first and foremost, that's what we're going to lead from the association's perspective. And then secondly, optimizing the system performance, because we want these systems to work and work great so that more people will want these systems to keep our industry working and working hard. And fundamentally, is there adequate interest in understanding the earth before the installation begins? The earth is not going to be uniform everywhere. Not only in terms of its heatability, but what's going to happen when the driller gets on site and starts putting wells in the ground. So what does the HVAC side need to understand about geology and hydrogeology? So that's kind of the way we've been trying to approach this. So we know what geology is. It gets into structure, rocks, and formations. Those are kind of the fundamental aspects that they're going to need to understand in these projects. Hydrogeology is the interrelationship of all those. So we're pulling those two things together, and specifically with soils, rocks, and water. So our motivation in this, and I want to give credit, we're not the first to think about this. Harvey Sachs, who did a lot of work with the Geothermal Heat Pump Consortium back in the 90s, has now moved on to other institutions, actually put together some guidelines for ASHRAE. There's a group in British Columbia, the British Columbia Geo Exchange Group, that's done some work. New York City, we find that hard to believe, but New York City has its own set of guidelines for putting in geothermal heat pump systems in New York City. And in the UK and the Netherlands, there's some guidelines as well. What we're doing is try to take the best of all that and then add to it. So what we're hoping to do is provide a tool for team members in a ground source heat pump installation. And we're talking large scale. We're not talking residential. We're talking commercial buildings, university campuses and the like, so that they understand what that geologic and hydrogeologic impact is going to be and how it's going to perform. We want this to improve the success of those projects. And unfortunately, there have been instances where we haven't been able to demonstrate the latter, but our goal is to create a growing number of examples where all this stuff comes together and time and money is saved and the project is saved. So this is from Nina Baird at Carnegie Mellon, some of her work with some open loop systems. And you can see that we have a water quality problem. And as she would explain, this was the condition when they started, and not too far into the project, this is what the water started to look like. And as a result, you end up with these kind of conditions, and performance is just going to decline. So it's that simple. And this is changes in the well screen intakes. You can see, you can see that they're just fouling due to water quality issues. The point being is that the architects just simply didn't think about a water quality aspect. It's just water. What difference does it make? Well, the quality of the water makes a big difference in terms of that system's performance over time. A New York City museum decided to go green, go to an open loop geothermal system, 2 300-foot supply wells, 2 return wells. Almost as soon as began, they started to get blockage in the system. And largely because the wells originally weren't sufficiently developed, and that quality issue, so they're blocking the intakes, and you can't get enough water back in the ground, and it just the problem just grew and grew and grew on top of itself. Now this is an unclosed loop, and it's Not a knowledge to any of you, but that's a little bit of an example of a quarry cut, but this shows you karst. And you can see this map of the United States where we have a lot of karst, including in Ohio. The geology staff at Ohio State tells a story that in the litigation, the university hired an expert that said there was no karst in Ohio. And the geology member said, then what are those caves that I take my students to every year? So you get into some bullheadedness. But here we get into loops that perhaps weren't adequately sealed at the surface. And as the grout settled, these little potholes started to surface, and the parking lot where the loop field was started to look like a golf ball with a lot of dimples, and had these little tiny sinkholes all across, and just inadequacy of the total construction project at the site, largely because of not understanding what was going to happen in the subsurface with the settlement of the materials. Now, this is Ohio State. This is what we call Bellagio East, Bellagio being the casino in Las Vegas that has the fountain show. And they were using air and injecting air into the surface to remove the cuttings. Well, in doing that, they started encountering these voids in the subsurface. That's going to go somewhere. So it's pushing that water out that was in there, and it was shooting out of all the open boreholes. And they had about 7 of these shooting water all over that part of campus during that drilling, which the university didn't like because it was distracting, it was messy, and it wasn't supposed to happen. So part of it was that it went into litigation. The contractor was removed, another contractor brought in, did a different drilling technology, was able to ultimately complete the project. Well construction problems. Again, when you get into the voids in the subsurface and you've got a grout, you've got a borehole volume of 450 gallons, but it took more than 1,000 gallons of grout. Now, you can say, well, okay, it took 1,000 gallons of grout. The problem is on a lot of these projects, the way the contracts are written, guess who eats that cost? The drilling contractor. That's totally unfair. He didn't make that condition. Mother Nature, God, whoever you want to assign it to, made that condition. One of the things that we've done as an association is earlier today there was a presentation by the Associated General Contractors who has a product called Consensus Docs. And several years ago, the association commented on those for large diameter, high production water wells and added some comments to get people to understand here is what a drilling contractor is going to encounter, that the contract terms have to be fair to them. Doesn't mean they have to be given an advantage, but they have to be fair. And we've done the same thing for geothermal heat pump projects as well. So that when this kind of condition happens in the subsurface, totally beyond the contractor's ability to control, they don't have to eat that additional cost of grout to make the job protect groundwater and make the system work the way it was supposed to. I guess there's the animation that went with it. This is part of the Ohio State project again. The original plan was $4.5 million to construct 480 geothermal wells on campus. Would save the university about $200,000 a year, and they calculated they would recoup their investment in 13 years. The new plan reduced the number of wells, and the cost went another $4 million up to deal with the geologic condition of the campus. The story State tells is that on another part of campus, they had put in a Future Farmers of America building, and it was geothermal, and they encountered the same kind of geology, had all these records, but nobody ever looked at them. And as a result, at least that's the story told. I'm not involved in it, so I don't know that factually, other than as the story is told. So again, some of the common geology and hydrogeology shortfalls is there's an assumption that the earth is uniform, and it clearly is not. Even at Ohio State, at that project, they drilled 2 test wells. My understanding is they were 25 feet apart. Odds are, you would think, oh, that covers it. Well, guess what? It didn't. It said the same thing. They'd gone 50 feet apart. They probably would have encountered different conditions. Just one of those things that happens. Lack of understanding of groundwater and its impact. One of the things we hear is that, geez, there's so many people on this job site already doing the geothermal. Do we really need a hydrogeologist on site? Well, maybe not on site, but you may need one involved to prevent those kinds of conditions happening. So it's their risk, but don't blame it on the drilling contractor when the system doesn't go the way it's supposed to. Some of the other issues is the lack of a single source responsibility, because there are so many different professions involved. Oftentimes, who do you really hold responsible for that? And inadequate construction monitoring. So much of that work obviously is below the ground, it's difficult to tell. And there's different things that you hear about, people count bags of grout and do the calculations, see if they actually grouted the hole enough or whatever. But it ultimately is that the driller has to drill to the design specification to the depth. The driller has to install the grout to the design specification, make sure the loop tube's installed, make sure the job's done right. And sometimes a misapplication of the technology. If the building envelope isn't understood, it's how much energy it's leaking or is inefficient, putting in a heat pump system isn't necessarily going to be the panacea. And then maybe only, as we saw in the open loop system, if you're only using it at certain times and not really understanding what's going to happen, oxygen can enter the system, and then you get into the precipitation of certain things like iron, which foul the system, and the system's efficiency goes down. Sometimes they're undersized. Rules of thumb. I'm not a practitioner. I've been around the industry for 30-some years. Kind of my pet phrase is the rule of thumb in the groundwater industry is there are no rules of thumb, because every project is unique. Every piece of ground is going to be unique. But clearly there are. But the mistake is to make the assumption that what we did on the last project is going to be the same as this project. And it just doesn't seem to be the case from what the professionals tell me. So you have to understand things like the load duration, the heat of compression, what's going to happen to it when it goes into the earth. So in our draft, and we're on like our 7th draft, this has been a long-term project, we're putting in some guidelines like this. So some general hydrogeologic considerations when choosing the heat exchanger and the drilling approach, and then a kind of a sample assessment methodology. The idea originally started out of, for those who are on the consulting side, you probably know of phase 1 environmental site assessments. The idea was to use that kind of same fundamental tool, but apply it to a geothermal heat pump project. Didn't go that way originally, but kind of 3.5 years later, kind of evolving back towards, maybe that wasn't such a bad approach in the first place. So some general drilling guidance. What we're not trying to teach drilling to architects and HVAC people, but we want them to understand that somebody that's going to try to do a certain kind of drilling technology in their bid proposal, does it make sense for that geologic setting, and does their price that they're quoting also make sense? Some relationship between the project team members, we're going to include that in there in terms of, okay, when this aspect is done, who does this and who holds accountability for it? The Geothermal Energy Organization, GEO, had a grant from the Department of Energy, and they specified in their research, it was to develop a national certification standard. There's 13 different professions that are involved at one time or another in a geothermal heat pump installation of the commercial scale. And then links to information about state requirements, permitting, and supporting references. We were a subcontractor to that GEO project, and our assignment was to go out to all the 50 states and create an inventory of all the regulatory oversight to all the different forms of installing ground source heat pump installation. So while the predominant methodology is to use a closed loop vertical borehole, there are also, of course, open loop vertical boreholes, but there's horizontal trenching, there's ponds, there's slinky systems, there's all kinds of different configurations, direct exchange. So what we tried to do was go to the states and say, where do you regulate this stuff? And then we built this database, and it's now part of the GEO website, and you actually can access it through the NGWA website as well. This is kind of a water analysis and interpretation, which really would apply only to the open loop systems, those that are installed. And a lot of people say, well, those just aren't the way it's done anymore. Well, actually, there's quite a few places it's still done, including standing column up in the New England area. You see a lot of standing column. Standing column being that you're taking the water from a borehole and returning that water to the same borehole just at a different depth and using it that way. It's a lot of hard rock, so it's very expensive to drill a lot of boreholes, so they try to do the standing column. So water quality would be a factor not only in an open loop system, but in a standing column system as well. Methodologies for assessing a site and geothermal heat exchanger options. So we're going to spell out some of those. So, as I said, this would be brief. Where are we at? We started on this in fall of 2011, and we had a group of volunteers that started on it in the winter of 2012, and they did some document review in the spring and started drafting documents in the summer. And like I said, we're on the 7th draft right now. We have a volunteer that's kind of being the master editor, so to speak, who's working on it, and his commitment is to have that final draft to us for more broad comment on January 1st. So that's where we're at in this process, and that's where we're going to be looking for more volunteers to come along. So that's what's involved. Again, I wasn't going to give you the answers because it's still in draft form as to what those guidelines are, but clearly we believe there's enough experience, unfortunately sometimes negative, that suggests there is clearly a value in understanding the geology and hydrogeologic conditions of a property before you get into building a large-scale heat pump installation. I was going to ask earlier, but I'll ask now, how many of you besides Ralph have done ground source heat pump installations in the room? Okay, quite a few of you, great. Anybody find any of this foreign to them, that they've never experienced any of these concerns? Everybody's seen this at some form or another? Yeah, every time I've given this talk, I see people nodding their heads going, oh yeah, and let me tell you about my story. So we think it is real, and it's unfortunate because it does create a bad sense. That story I relayed about the consultant in New England that was with the gasoline plume, he said the end result was the architect, the HVAC contractor, and the remodeler of the building all vowed they would never do another geothermal heat pump project again. Well, that's a lot of lost opportunity, lost experience, bad word of mouth. What's the rule of thumb? If you have a bad experience, you'll tell 5 or 10 people. If you have a good experience, you might tell 1. What's that, 15?
The rules are 250 and 2. You have a bad one, kill 250, you have a good one, and get you 2.
There you go. So that's our motivation as an association. Even though it's only a portion of what our industry does, it's kind of tangential, it's a diversification, but we're trying to do those things that first and foremost protect groundwater, because that is the lifeblood of our industry. That's what everybody makes their living from day in and day out. But we also want these systems to be successful so that diversification opportunity stays in place. Won't guarantee that this will make a difference, but it's better to do something than do nothing. And that's been our attitude about it. Comments or questions? Any stories anybody wants to share? Or disagreements? We're open to those too. See, that's the good thing about coming at 2:45. Everybody's, yes sir, in the back.
Yeah, hi, I'm Russ Bell. I went to Iowa DNR. I'm a former well contractor myself with the geothermal. I'm a former master water well contractor information organization. I now manage the Iowa private well program, including the geothermal system. And one of the things we had up there was an our-home area for the city of Marion, or the school system that we had in Iowa. And that system, one of those potholes where it was like a golf ball, they had over $120,000 in repairing the settling spot in their loop field before they decided it was time to bring other people in and do the investigation. And in the end, they had about $800,000 in moving parking lots and site restoration and monitoring involved. So, I mean, it's a large commitment for a school system. And we heard similar comments that the schools, even though they had other successful geothermal systems, they were a little gun shy of looking at geothermal again. And we've been doing something very similar to the program the NGWA is proposing here for the last 4 years. And it's taken a lot to get the engineering firms and the architectural firms on board that it needs investigation on all these sides. A third of Iowa really does fall in an area that could be considered forest. And that, if we could lock that third of our state off, my program would be a lot easier to run. Because that is a difficult area. But we've made made a lot of strides in it, and even though it's not a perfect system yet, we can show that implementing this kind of protocol, it improves communication to all the parties involved. It makes drillers happy, the engineers and architects and the owner just understand that there may be extended costs when you pull on the site. And it even has, I would say, it's raised morale of the workers on geothermal sites because there was pressure to pull a rabbit out of your hat.
Right, right.
So I'm a big advocate of this. I have a lot of stories I can tell along the same line.
Thank you for sharing that, Russ. Yes, sir.
The biggest problem is the architects and engineers. If they decide they're going to have a geothermal project and they just put it out for bid and nobody ever does any test work on it.
Mm-hmm.
I mean, I've been on 3 or 4 jobs where they had, you go out there and drill us 500 holes and they don't know what's out there.
Right, right. And there, obviously, that whole profession, both of those professions, that isn't universally true, but it's true enough that these kinds of things, including like what Iowa is doing, are necessary to make sure that the future of this opportunity is positive, is bright. Anyone else over here?
Kentucky
Yep.
has one of those problems also, and Scotland doesn't move toward seeking legislation to deal with, to have a closed loop borehole installations.
Biggest problem they got out there is methane gas.
Certified driller is required to do the drilling?
Yes.
Okay.
And through the regulation promulgation, we'll be looking to address the geology.
Right. The International Ground Source Heat Pump Association has a driller accreditation program. You take a course, take an open book exam. If you pass it, you're accredited by them. We take a different approach. We have our certified vertical closed loop driller program. We recognize that that's different than a water well. The drilling part is very similar, but obviously when you start to add casing and screen, then it changes. So we took all those aspects out, but we do certify, and part of our certification program is that you have to demonstrate that you have 2 years of competency behind the drill rig, that you know how to run a drill rig, and you're not somebody that came from auto mechanic school or something and suddenly you're an accredited driller even though you've never seen a drill rig in your life. There's a place for both. Someone else? Yes, sir.
The guy from Iowa was speaking, and I went to a CU class on Groundwater in Idaho, and I think it was Nebraska, your neighbor, did a big study on drought and how well it's healed. And it just really was amazing how terrible most droughts do in the dry zone. So, it's like most of the geothermal some form of bentonite drought, and in the dry zone, like above the water table, that stuff just puckers up. It's kind of useless to see.
My recollection, I'm not authoritative on the study, I'm aware of it, is the chip grouts, chip bentonites work the most effectively. Yeah.
That was the end result of the study.
Right.
Even they didn't do so well in the dry zone, it's hard to get them hydrated and mixed.
Right.
We pump a lot of bitnight, soap and sand, 2,000 pounds of sand, 5 bags of bitnight.
Right.
That's most of the thermal conductivity, isn't it? Hold up and
Because I remember in the Nebraska study, it wasn't necessarily the chips that were important, that's just the form of it, it was the solid content of it.
I see.
The structure was midnight to hold to.
Okay.
So in the NATO zone, the high solids thermally came around. And I remember right, that's supposed to that involved in.
It performs better than 26% solids. But it didn't perform as well as the chips, which were 60 to 80% solids. But on a thermal conductivity standpoint, the chips performed like a 0.44, so it's like an average to dry clay. Very poor for a design standpoint on the system.
And that was in the beta, so I,
Well, anyway, it'll be the same.
I write down the saturated.
If you spot a fellow with a name badge that says Tom Christofferson, Tom was the lead from the state of Nebraska for that study, and he's here. So if you see Tom, You can ask him, and he can expand upon it. He was our McCray lecturer on that a couple of years ago, and shared that research around the country. And it goes beyond heat pumps; it goes to water wells as well.
What was interesting on that project is that it all stemmed from the fact that they thought that more annulus was better, to have a better seal.
Right.
And so then they put in the low cost and annulus started falling in, and all the panic, what do we do? I said, well, smaller hole, less cracks, and I mean, less this might.
Yep.
What happens to a dry pond, you have bigger cracks, and you have bigger surface, more cracks.
Right.
That's why the study is made, because they had to go, we had to have bigger annulus.
Right. There's state of California, right, Mike? They're presently developing regulations, and that's one of the issues: is how big is the borehole going to be in order to properly place the grout. Right. At the end of the day, it's got to achieve what it's supposed to do, and it's prevent surface migration to the subsurface and commingling of aquifers. That's the grout's purpose in a borehole. Other comments or? Okay, great.